Welcome to this lecture. In this, we will introduce another example of first order systems. Earlier, we discussed thermometer as an example of first order system. Now, liquid level in a tank. So, this is another example of first order system. So, let us consider a simple tank through which a liquid is flowing in, the liquid flowing in and flowing out. It's a tank of uniform area of cross section. The area of cross section A is constant. Q is the inlet volumetric flow rate, Q0 is outlet volumetric flow rate, and H is the height of the liquid at any instant in the tank. The outlet here may consist of, can be anything. It can be a pipe, it can be a pipe fitted with a valve or a weir or a notch. So it can be anything. So the relationship, there is no other driving force here, only the liquid head is the driving force. So this flow rate, outlet flow rate, what does it depend upon? It depends upon the height and the resistance. Resistance. What is resistance? The outlet, whether it consists of a pipe or a weir or a valve, anything, whatever it may consist of, it has got a resistance for flow. That resistance is denoted by R. Resistance is denoted by R. R is the resistance. So the relation between Q0, H and R is known as the flow head relation. So Q0 will be a function of the height and the resistance. More the height, more will be the flow rate, outlet flow rate. More the resistance, less will be the flow rate. Resistance opposes the flow. So Q0 is a function of H and R, the flow head relation. So the exact relation depends upon the type of outlet, the condition of flow condition. For example, it can be a Q, in some cases Q0 will be directly proportional to H, the flow directly proportional to H. This is H, this is proportional to Q0 proportional to H. For example, Q0 can be equal to H by R. That is if the outlet consists of a simple pipeline and the flow is laminar. So under laminar flow conditions through a pipeline, the flow head relationship will be like this, directly proportional to H, Q0 equal to H by R. So this is known as a linear relation. So Q0 is directly proportional to H. So it may not be always the case. In some cases, Q0 will be proportional to H power n, where n is not equal to 1. N is any constant other than 1. So this is a non-linear relation. So it can happen if the flow, if this is a pipeline and if the flow is under turbulent conditions through a pipeline or through a valve, then, or a weir or notch, then it will be, n will not be equal to 1. It will be some constant other than 1. For example, if it is a turbulent flow through a pipeline or a valve, then n will be equal to 0.5. So Q0 will be equal to C. C is a constant into H power 0.5. So under turbulent flow, under turbulent conditions, turbulent flow through a pipe or a valve, Q0 will be equal to C into H power 0.5. In some other cases, in weirs, the constant can be something else. For example, it can be 1.5. So basically it is n is not equal to 1. So this is known as a non-linear relation. And this is a linear relation. So now when you give a change, when there is a disturbance in the inlet flow Q, what can happen? Number one, the height will change. If there is a change in Q, the height will change. Similarly, the outlet flow also can change. So a change in inlet flow, change in inlet volumetric flow rate can cause a change in both these variables Q0 as well as H. So there will be two transfer functions, number one relating Q and H, and another transfer function relating Q and Q0. So here the input variable from dynamics point of view is the inlet flow rate Q. The response variable or output variable is, number one, it can be height, and number two, it can be the outlet flow rate. So there will be two transfer functions relating, number one, Q and H, and number two, relating Q and Q0. So both of them, each of them will be first order transfer function of the form K by tau s plus 1. And they can be derived easily, directly it can be derived provided the flow head relationship is linear. So if the flow head relationship is linear, these transfer functions Q and H and also Q and Q0 can be derived directly by making material balance. In case it is a non-linear relation, if the flow head relation is non-linear, it may not be possible to derive the transfer function. You need some modification. You need some modification of this non-linear relation to a linear relation. In case it is non-linear, we need some modifications to be done. We need to modify this non-linear relation. We have to, under approximate conditions, we have to approximate this non-linear relation into a linear relation. Only then transfer function can be derived. Transfer function can be derived only for linear relations. So if you have a non-linear relation, first it has to be linearized and then it has to be linearized and brought to this form, and then we can derive the transfer function relating Q and H and also relating Q and Q0. So this is about the concept of liquid level in the tank. What are the transfer functions in this, and what are the relationship, how the relationship flow head relation is going to affect the transfer function. If the flow head relation is linear, transfer function can be directly derived. If it is non-linear, then first it has to be some modification is to be done for this relationship. It has to be approximated into a linear relation and then derived. So we'll see about this derivation in the subsequent class.